Oh, now we're live. Okay, great. Yes, this should work.
In theory, we're not restricted by time, so we can go for time.
Okay.
And
Yeah.
Oh yeah, we are live.
Okay. Yeah. If you want to write, you just, I think you know the step.
How does it work?
Hmm?
I mean, the screen's not changing when I do change things.
Why not? Okay, well, now it should be changing.
Oh yes, good.
Yeah.
How do you take out your pen?
Just the other side.
Yep. Oops.
Our attendance is dropping.
Is the live working? Is it working? Can you check?
It should be. Yeah, it's working.
Do I need a mic?
I mean, you have to the light audience, right?
No, you don't need a mic, I think.
Oh, will my voice project enough?
Hello.
Alright, just start. Alright, let's get started with Math1231 and 1231 revision seminar part 2. So we have this thing called Super Revision Day coming up. So you can scan this QR code if you are interested in it. The way it works is you go and then these past people will help you study for the final exam, basically. This is our attendance form. So it would be great if everybody scanned this. Alright. So this is our overview of our topics. We'll start with the first topic, functions of several variables. So we're going to be starting with partial differentiation here. So what we've been doing so far before this course is we've been looking at 2D curves where we have like a function of just one variable, f of x. But what if now I have a function of multiple variables, like f of x and y, and I want to differentiate, that is, I want to find the gradient of the tangent specifically to just one direction, either the x direction or the y direction. This is where partial differentiation comes in. Because we're only focusing on one direction, we hold the other variables constant. So in this example above, if we have f xy equals x cubed plus xy, it's y cubed. If I want to do partial f with respect to x, I can differentiate x cubed normally to get 3x squared, but xy, since y is a constant, doing partial of this is just going to give me y back. Similarly, if I partial with respect to y, the x cubed, it's a constant, so it gets sent to 0. Xy becomes x, and y cubed just becomes 3y squared. Now, how can we use this? We have this thing called the mixed derivative theorem. So if f is a function of two variables, and if f and all of its first order and second order partial derivatives are continuous, then we have this. Now, what this means is, say I have a function f, and I do the partial derivative with respect to x first, and then I do it with respect to y. We get this here. But if I were to do it with respect to y first, and then with respect to x, the theorem states that it doesn't actually matter which order you do it in. So here, how can we use that for this question So if I have fx and y be x squared y squared plus this horrible expression here, we can notice all of this is in terms of y. Now if I want to differentiate that in terms of y, it's going to take a long time. So instead what we can do is we can perform partial f with respect to x first. Because when we partial with respect to x, all the y's are treated as a constant. So differentiating a constant gets sent to 0. So if we do partial f with respect to x first, the e thing here will all be 0. The x squared y squared gets turned into 2y squared x squared. And then partialing that with respect to y, we get 4xy. So the mixed derivative theorem tells us we can actually do it in any order we want. Now, how can we use that here? We have something called a tangent plane to surfaces. So when we were working in the 2D world, we would have something that looks like this, 2D. And if I want to find the gradient of the tangent, it looks something like this. However, when we're working with multiple variables like x, y, and z, and we have some kind of surface, and I would say using partial differentiation, I can find the gradient of the tangent specifically at this x direction. Well, using what we know, we can actually find the tangent plane in this direction. So if we're given a function in the form f x y z equals 0, the normal vector at the point P, so let's say I call this point here P, the normal vector, which is given by this, is partial f in respect to x, respect to y, respect to z at P. And then we can use the definition of a plane, the point normal representation of the plane, and then we can find the Cartesian equation from this. So if I have a surface z equals 3xy squared and I have a point 1, 2, 12, how do we find a normal vector? Well, we can notice we want it to be in the form f x y z equals 0. So moving the z to the other side, we have 3xy squared minus z equals 0. That means I know that the normal vector is going to be given by the partial with respect to x, the partial with respect to y, and the partial with respect to z. So with respect to x, the 3y squared is considered a constant, so it's going to be 3y squared. And with partial y, the 3x is a constant, so it's going to be 6xy. And this one becomes minus 1. But we want to evaluate it at P, which is given by 1, 2, 12. So we substitute these values in to get n is equal to 12, 12, 1. 12, 12 minus 1. So that's how we find the normal vector. Now we want to find the Cartesian equation. So we use our point normal form of a plane where we do 12, 12 minus 1. We dot product it with any vector on the plane minus the point 1, 2, 12. And this has to equal 0 because the normal vector is perpendicular to any vector on the plane. So expanding all of this out, okay, yeah.
Sorry guys, some technical issues. We'll quickly fix it. It's just not showing full screen. I personally think it's because we made this too small, and too big. Okay, surely this works. Let's try again.
Yep, so recalling the point normal form of the tangent plane, substituting in, we have this, and that is our Cartesian equation of the tangent plane. Now we're going to be moving on to total differential approximation. So it says that if we have some f that's a function of two variables, the total change in f is approximately equal to the partial with respect to x times by the change in x plus the partial with respect to y times the change in y. So what that means is if I have some f that is with respect to two variables x, y, and I told you, okay, x went up by some amount and y went down by some amount, what can you tell me about f? How much does f change? That is what this formula is used for. So, oh yeah, and there's this part here called error estimation. If we want to find the upper bound of the error, we can put an absolute value on both sides. And then by the triangle inequality, it's going to be smaller than or equal to the absolute value of each term added up. So now let's look at this question here. The area A of a rectangle with length x and y with y is given by a equals xy. We want to use the total differential approximation for a as a function of x and y to estimate the percentage increase in a when x increases by 5% and y decreases by 6%. So if I want to use the formula, it's going to be the total change in y. It's going to be approximately the partial a with respect to x times by the actual change in x plus partial a on partial y times by the change in y. So what we have to do is find what each of them are. I know a is equal to xy. That means the partial with respect to x means we keep y's constant. So we're just going to get y. And partial a with respect to y, we keep the x's constant. So it's going to get x. We're given that x increases by 5%. So if it increases by 5%, that means the change in x is going to be positive 0.05x. Now if y decreases by 6%, that means the change in y is going to be minus 0.06y. So putting that all into here, we get the change in a is approximately, so we have y 0.05x plus x minus 0.06y. So that's 0.05xy minus 0.06xy, which is minus 0.01xy. But remember that a equals xy, so this is equal to minus 0.01a. So I can see that the change in a is approximately equal to minus 0.01a. So it tells me that a decreases by approximately 1%. So that is how we can use the total differential approximation. So yeah, this is what we did. We have 0.05 minus 0.06. So therefore it's a 1% decrease. Now we're going to be looking at the chain rule. So there's lots of different types of chain rules. So the way it works is if I have some function x, y, and x is, let's say in terms of t, then we're given this formula. And the way you can intuitively find this formula is you can draw a kind of graph here. So I have some function x, and it's going to be in terms of x and y. But we're told that x is a function of t, and y is also a function of t. So that means both x and y are going to go to t. So if I want to find the total diff of f with respect to t, I can go two ways. I can go up and down. So that way, since f is a function of x and y, it's going to be partial f on partial x on the top. And going from x to t, since x is only a function of t, it's going to be the normal dx on dt. I can also go the bottom way, which is partial f on partial y and dy on dt. Now adding these two up gives me df on dt. So yeah, drawing a graph makes the process more intuitive rather than just memorizing formulas. So let's look at another one here. If I have fxy and x is a function of s and t, same with y, drawing it out, f goes to x and y, and both x and y, they go to s and t. So I can see that. Let's just do an example. If I want to go from f to s, so say partial f with respect to s, I can go to x first, like this, and then I can go from x to s, like this, or I can go down to y, and then I can go back up to s. So this is how we intuitively find the chain rule. This is for t. We can go up to x, down to t, or we can go down to y and then down to t as well. So let's have a look at this one. So f is only in terms of u, but u splits off into x and y. That means if I want to find the partial f with respect to x, we have to go to u first, and then to x. If I want to go to y, we go to u, and then we go to y. Now we have a triple chain rule here. So if f splits off into x, y, z, which splits into s and t and splits into u, the way we want to find, for example, just going to df to du, or there's multiple ways. We can go to x, s, u, x, t, u. So you want to find basically all the ways to get it and add them all together. So that's how the chain rule works. Memorizing this is honestly horrible. Doesn't look great to memorize. So drawing a diagram and then following each path makes it easier. So let's have a look at this question here. Oh yeah.
It was a bit cropped before.
Alright, now let's have a look at practice question. So we're given z is a function of x and y. X is given by r cos theta, y is given by r sin theta, and we want to find partial z with respect to r. So I don't know the chain rule, so I want to draw a graph first. So I know z is going to split off into x and y, and I know x and y, they're both going to go to r and theta. So if I want to find just going to r, that means dz dr can be, or I can go the top route and then go straight ahead, or I can go to y and then go back up. So I want to find all of this and plug it into the formula. So let's see. If I have x is equal to r cos theta, partialing x with respect to r is just going to give me cos theta. And if I have y is equal to r sin theta, partial y with respect to r is just going to give me sin theta. Now we have z is equal to e to the xy plus x squared y. Doing the partial with respect to x means we keep the y as a constant. So the y in the exponent is going to jump to the front. So it's going to be this. And x squared is constant, so it's going to be x squared. Now we have dz on dy. Similarly, x is a constant, so x moves to the front. And y is a constant, so 2xy. Now I want to find everything at r is equal to 1 and theta is equal to pi on 4. So the way it works is after we find everything, we want to substitute r equals 1 and theta equals pi on 4. So for x, we have 1 over 2, and for y, we also have 1 over 2. And e to the xy is e to the half, and we substitute all of those into our partial derivatives. And putting that into our formula, which is just brute forcing, we get this as our final answer. So that is how we can use the chain rule. So all good so far? Alright, so now we're moving on to the next topic, bunch of integration techniques. Yeah. Okay, don't zoom in. Okay.
Yeah, yeah. Okay. And then a full screen, you reckon?
Right, so integration techniques. So I'm just going to be going through a bunch of different types of integrals you can find and how to deal with them. So we have some trigonometric integrals where it's going to be a product of sine and cos, and each of them are raised to a specific power. So in the first case, where n is odd, what you want to do is you want to let u equal sine x, because that way the du is going to be cos x dx, and you want to use this trig identity here. So if I were to give an example, so if n is going to be odd, so let's do something like sine squared x cos cubed x dx. So I can see m is 2, n is 3. So I want to split it into cos x, cos squared x dx, because I want to use this formula at the bottom here. So I turn it into 1 minus sine squared x. Now if I use the substitution u equals sine x here, the sine squared becomes u squared, the 1 minus sine squared becomes 1 minus u squared, and the cos x dx becomes du. And this becomes something much easier to integrate. Now it's a similar case, but when m is odd, this time you let u is equal to cos x, and we use this trig identity here. However, when they're both even, we can't split it into, like I did, cos x, cos squared x anymore, because they're both even. So we want to be using these two identities. So I'll show you with the evens. So if I have integral of sine to the power 4x, I know that sine to the power 4x is going to be sine squared x or squared dx. Now using my identity that sine squared x is half 1 minus cos 2x, this is going to be half 1 minus cos 2x all squared dx. Oh, whoops. So this is going to be a quarter 1 minus cos 2x squared dx. So moving the quarter to the outside, 1 minus 2 cos 2x plus cos squared 2x dx. Now I can integrate 1 and cos 2x fine, but now we have another issue where we have another trig where it's to an even power. So we want to use this identity again. It's going to be a quarter 1 minus 2 cos 2x plus cos squared 2x. It's going to be half 1 plus cos 4x. So it's going to be double the angle. Like notice how the x becomes 2x. 2x is going to become 4x. So now I'm going to take out half again. So it's going to be 2 minus 4 cos 2x plus 1 plus cos 4x. So that's 1/8. 3 minus 4 cos 2x plus cos 4x dx. And now this is something I can integrate. So it's 1/8. 3x minus 2 sine 2x plus sine 4x on 4 plus c. Now expanding that all out, this is our final answer. So we see we changed the sine squared into 1 minus cos 2x on 2. We expanded it, and then we changed the cos squared 2x into this here, into something we can integrate. Here are some more trig integrals. This time we have mx and nx here. So it's just 3 cases. If it's sine and cos, it's going to be sine m plus n plus sine m minus n. If it's cos, it's going to be cos m plus n plus cos m minus n. And sine, it's cos m minus n minus cos m plus n. So it's just formula bashing. That's what it is. So I want to use these cases here. So I see that it's a sine cos. So that means I want to use the formula half sine m plus nx plus sine m minus nx. So here I see that m is going to be 3 and n is going to be 2. So the integral is going to be half sine 3 plus 2x plus sine 3 minus 2x dx, which is half sine 5x plus sine x dx. Now I can integrate this. So that's going to give me minus cos 5x 5 minus cos x c. So that's our integral. All we did was just use the formula, and then we got something that we can integrate, sine 5x and c. Now we have some other trig identities that are important, which is 1 plus tan squared is sec squared. And you should know the derivatives of tan x, which is sec squared x, and sec x, which is sec x tan x. So how can I use that? If I have an integral like this, well, notice I can split this into sec cubed x times sec x tan x dx. Now what I can do, if I do the u sub, u equals sec cubed x, sorry, not sec cubed x, just sec x, that means du on dx is going to be sec x tan x, which is right here. So I can rewrite the integral as u cubed du, because sec x tan x dx is du. So then this is just a quarter u to the power 4 plus c, which is sec to the power 4x on 4 plus c. So that's how we can use trig identities. Now we have something called reduction. Now the way reduction works is we're given some integral in terms of n, and I want to turn it into some kind of recursive formula where we have in and in plus 1 or in minus 1 sometimes. Now the way you do it is normally you do it by integration by parts. So if I have in is equal to 0 to 1, 1 over 1 plus x squared to the n dx. What you let u is normally the term that has the n in it. So I'm going to let u equal 1 over 1 plus x squared to the n. So that's just 1 plus x squared to the minus n. So du is going to be minus n 1 plus x squared minus n minus 1 times 2x dx. And dv is going to be whatever's left, which is 1 dx, because we have nothing else there. So v is going to be x. Now I want to plug it into the by parts formula, which is uv minus v du. So it's going to be, so in, so uv, so uv, so x on 1 plus x squared power n from 0 to 1, because our integral is bounded from 0 to 1, minus 0 to 1, v, that's x, and du. So that's minus n 1 plus x squared to the minus n minus 1 times 2x dx. So on the left here, substituting 1 in, you get 1 over 1 plus 1, which is 2 to the n, minus 0 over 1 plus 0 to the n. So that's just going to be 0. On the right here, we have minus n and a 2. So if I bring minus 2n on the outside, the minus here becomes plus 2n. 0, 1. The x and the x multiply to give x squared, and this stays the same. So now I look back at the formula and I see that it's all in terms of in and in plus 1. So that means I want my answer to be in this form here. So I'm pretty close with the x squared. So what I can do is I can change it to 1 plus x squared minus 1. times 1 plus x squared to the minus n minus 1 dx. What that does is it allows me to multiply 1 plus x squared here, and minus 1 with 1 plus x squared. Now what that looks like is 1 over 2 to the n plus 2n. These guys multiply to give me minus n, and these guys multiply to give me minus n minus 1 dx. Now notice, these guys are now in the form of the original in. That means I can change it to 2n. This is in, and the right is in plus 1. So in is going to be 1 over 2 to the n plus 2n in minus 2n in plus 1. Rearranging, so that's 2n in plus 1, going to be 1 over 2 to the n plus 2n minus 1 over in. And then finally dividing by 2n on both sides, we get what we want. So the overall gist you can get from this is use integration by parts. We want to let u equal the term that has the n. And then if we get stuck here, we can use this trick where we do 1 plus and then minus 1 and expand to get back into the form in. So this is, yep. Oh no, it's okay. So yep, we have in plus 1 here, and then rearranging, we get our answer. Now here are some other substitutions that depend on what our integral looks like. So if it's a squared minus x squared, we use this substitution or this hyperbolic trig one. Now the way we get it from is, if say I have sine squared theta plus cos squared theta equals 1, that means cos squared theta is going to be 1 minus sine squared theta, which resembles a squared minus x squared. That's why we let x equal a sine theta here. And using the other trig identities, we get a tan theta and a sec theta for the other ones as well. And also the hyperbolic ones. So if I want to use that here, I want to look at what's inside the square root. And here it's in the form x squared minus a squared. And the substitution we can use for that is a sec theta or a cos theta. So I'm going to just do the substitution a sec theta. So here a is 1 because it's minus 1. So it's going to be x equals sec theta. Dx on d theta, from before, the diff of sec was sec theta tan theta. So that means this integral can just be, or x is sec theta. This becomes sec squared theta minus 1. And on the top is sec theta tan theta d theta. So the sec on the top and bottom cancel out. Sec squared theta minus 1 is tan squared theta. So you get tan theta on root tan squared theta d theta. Root tan squared theta is just tan theta. So they're going to cancel off the top and bottom. And we're left with just d theta, which is theta plus c. But remember, x was sec theta. So that means this is just going to be sec inverse x plus c. So we can see that here. They did the same thing. They let x equal sec theta because it's in the form x squared minus a squared. Now we have another thing called partial fractions. Now we're given this partial fraction decomposition to find this integral here. So that means that integral is going to be 2 over x plus 3 plus x minus 5 on x squared plus 2 dx. So this on the left is just a simple 2 ln x plus 3. However, integral on the right, I have to split it into x on x squared plus 2 minus 5 on x squared plus 2 dx. So this one here, so multiplying by 2 and dividing by half for this one, we're going to get half ln x squared plus 2. And the right one is a simple arctan integral. which is just more formula basically. So that's how we use partial fractions right here. So this, the arctan is in a squared plus x squared, so it's 1 on a tan inverse x on a. That's how we get this here. Alright, so that's all good. We're going to be going on to the next section, ODEs. So there's different types here. We have separable, first order, linear, exact. Yeah. So the first and easiest type is called separable. So it's where dy and dx is in the form g of x, h of y, because we can separate it and move the same variables to one side. For example, I can move the y squared to the left, and I can move the x power 4 to the right. And then I can integrate both separately. That's why it's called separable. Now there's a cool substitution technique you can use. If our ODE is in the form y on x, so it's composed of y on x's, we can actually use the substitution y equals x v. And what it does, it transforms it into a separable one. Now how do we check this? fxy can be written in this form. It's composed of y on x, if and only if fxy equals f lambda x lambda y. What this means is, since dy and dx is a function of the ratio between y and x, it only works if fxy and f lambda x lambda y are the same. Because we're only talking about the ratio between y and x here. So now how can we use that? Well, I can see xy plus y squared on x squared. I can rewrite this as xy on x squared plus y squared on x squared, which is y on x plus y on x squared. Now, since dy and dx is in terms of y and x, I can use the substitution y is equal to vx. So that means dy and dx is going to be, well, diff of x, which is 1, times v, plus diff of v, so that's dv on dx, times x. So I can just put that all back in. So dy on dx is v plus x dv on dx. Y on x, so from here, y on x is going to be v. It's going to be v plus v squared. Now subtracting v on both sides, you get x dv on dx equals v squared. So now we have a separable one, because I can move 1 on v squared to the other side, and move the 1 on x to the other side, and I can integrate both. So it's minus 1 on v equals ln x plus c. However, the question asks, we want it in terms of y. So, since v is equal to y on x, I want to put that back in. So it's going to be minus 1 on y on x equals ln x plus c. And then rearranging it, so that's our substitution. We get y is equal to minus x on ln x plus c. So that is how, because it was in the form y of x, we can use y is equal to vx and then turn it into something separable, like here. Yeah, if you don't want to do this, you can use maple, which is more reliable, to be honest. Now we have something called first order linear. So it's in this form. So we have dy and dx. Notice how it's dy and dx. It's not d squared y. It's just dy and dx plus some function in terms of x multiplied by y equals g of x. It's kind of in this form here. And the way we solve it is we multiply both sides by something called the integrating factor. So the way it works is we just look at the term next to the y. And we're going to find e to the integral of f of x dx. And after you find that, you multiply both sides of the equation by this. And then you get something that looks like this. So imagine if h of x was the integrating factor. By the product rule, this is the same thing as d of dx, h of x times y. Because if you notice, diff of y, h of x, and then diff of h of x, y. And then you can integrate both sides. So we're going to be using, so this is what an example looks like. So I can see it's a first order linear because it's dy and dx on its own. It's not a second order. We have some function of x, it's in terms of y, and I have some function of x here. So I want to multiply by the integrating factor, which we just look at the term next to y, and we find e to the integral of that term right there. So this integral here is another ln, so it's e to the half ln 1 minus x squared, and that turns into just 1 minus x squared, root 1 minus x squared, sorry. Now this is our integrating factor. We want to multiply both sides by it, because then what we get is, I'll just write it here, we get root 1 minus x squared dy dx minus x on 1 minus x squared root 1 minus x squared y is equal to 2 1 minus x squared root 1 minus x squared. Now this here on the left can be transformed into a product rule of root 1 minus x squared. So this was our integrating factor times y, and this was our right hand side. Now the way why we do this is because since we have something in this form, I can just simply integrate both sides with respect to x, and this on the left just stays as root 1 minus y squared y. And integrating the right side, we get 2 arc sine x. So therefore this becomes our final equation. Now we sub in our initial condition to find that c is 1, and therefore this is our final answer. So this is how first order linear works. All in all, you just get the function next to the y, you raise it to the e power, you integrate it, multiply both sides, and then you can product rule the left hand side, and then integrate both sides like normal. Now we have something called exact ODE, and they're in the form fxy plus gxy dy dx equals 0. And we can check if it's exact if the partial f with respect to y is equal to the partial g with respect to x. If it is exact, that means the solution to the ODE is hxy equals some constant, where partialing h with respect to x gives me f back, and partialing h with respect to y gives me g. So let's see how we can use that for this question here. So show that it's going to be exact. Well, I can see that this right here is going to be our fxy, this right here is going to be gxy, and I said it's going to be exact if the partial f with respect to y is equal to the partial g with respect to x. So since f is tan y minus 2x, partialing this with respect to y, 2x is a constant, so it's just going to be sec squared y, and since g is x sec squared y minus 2y, since y is a constant, it's just going to be, so it's just going to be sec squared y. Now since they're both sec squared y, and they're equal, we see that the equation is exact. Now I want to find the general solution, so remember, the general solution, h, x, y equals c, works. When partialing this with respect to x, we get f back, and partialing this with respect to y, we get g back. Yep, so the partial with respect to x is going to give us f, and the partial with respect to y is going to give us g. And the way we can do it is we can integrate this side, so it's going to give me h, x, y back, but we integrate it treating y as a constant. Since tan y is a constant, to integrate a constant, we just chuck an x in front of it, minus 2x, just because minus x squared, and we have a constant. Now the reason we write c1y is because since we treated all the y's as a constant, our constant here could be a function of y, we don't know. Now we can differentiate partially again with respect to y to get h of y again. So it's x squared y, then x squared gets sent to 0 since x is a constant. Now we have the diff here. Now, comparing equations 2 and 3, so it's this one and this one, we see that the x squared y is equal. So therefore, minus 2y has to be the diff of the constant. So C1 diff y is minus 2y. Just integrating both sides, that means it's minus y squared. We can ignore C2 here, which is the constant when we're integrating, because our general solution is already equal to a constant. So the constant is going to disappear. So therefore, h of xy is going to be what we found earlier, x tan y minus x squared minus y squared, which was our constant. So this is our exact solution. Now we have second order homogeneous. We know it's second order because the diff here is a double diff, and it's homogeneous because it's equal to 0 on the right side. Now the way we do it is we use a substitution a e to the lambda x. Substituting in, well, we can factor a e to the lambda x out, and we get lambda squared plus a lambda plus b equals 0. So unless a is 0, that means this right side has to equal 0. Now what do we get? We get something called a characteristic equation, which is a quadratic. And then we can just solve this quadratic normally to find the two values, or the values of lambda. Now, after solving the characteristic equation, lambda squared plus a lambda plus b equals 0, there's three scenarios. We could get two different real lambda. If that's the case, you put it with a e to the lambda and b e to the lambda x. However, if we only have one lambda, for example, we could have lambda 1 squared equals 0, lambda equals like 1. That means we do the same thing except we attach an x to one of them. So y is going to be a e to the 1x plus b x e to the 1x for this. Now if there's two complex conjugate roots, then our general solution is going to be e to the real part x times a cos beta x plus b sine beta x. Yep, so I want to be writing down the general solution to this right here. So the way we do it is I want to write the characteristic equation first, and we do it by looking at the coefficients of these guys. So that's lambda squared plus 4 lambda plus 4 equals 0. Solving it, you get lambda plus 2 squared equals 0. Lambda has to equal minus 2. So if there's only one root or one solution for lambda, that means the solution for y has to be a e to the minus 2x, since lambda is minus 2, plus not just be, but bx e to the minus 2x. Now I want to use my condition here, that y0 is going to be 0. So substituting 0 in, you get 0 equals a e to the 0 plus b0 e to the 0. So b times 0 is going to be 0. E to the 0 is going to be 1. So we get a equals 0. Therefore, our general solution is just going to be bx e to the minus 2x, like so. Yep, since it's a repeated root, we're going to be using this general solution form. We get a equals 0, so therefore this is our final solution. Now this time, we could get something where it's not going to be equal to 0, but instead equal to some function of x. Now the way we do it is, we imagine it is equal to 0 first to find the homogeneous solution. Now the way we do it is just normal. We write the characteristic equation, we put it into one of the three general forms, but then we want to find a particular solution, because our answer y is going to be the homogeneous solution plus the particular one. Now the way we find the particular one, the particular solution is always going to be in the same form as f of x. So depending on what f of x is, we make a guess for what the particular solution is going to be. So for example, if it's a polynomial, like say we have something here, and it's equal to some polynomial like x squared plus 2. That means our guess for the particular solution is going to be some general polynomial that has the same degree. And we put this back into our ODE, and we can solve for A, B, and C. Now, these are some common guesses. If it's an exponential, you also guess an exponential. If it's a cos or a sine, we guess cos plus sine, and so forth. So I want to solve this initial value problem here. I can see it's non-homogeneous since it's equal to, well, not zero. So the way I do it, first, I want to find the characteristic equation first. So this is going to be lambda squared minus 5 lambda plus 6 equals 0. That's lambda minus 2, lambda minus 3 equals 0. So let's get lambda equals 2, 3. So that means my homogeneous solution is a e to the 2x plus b e to the 3x. But since this is not equal to 0, it's equal to some function of x, I have to make a guess to what the particular solution is going to be. Now remember, if it was some kind of exponential, I want to guess the exponential of the same form. So e to the 2x, so I want to guess maybe a e to the 2x. But you have to note that the particular solution and the homogeneous solution have to be in different forms. Because if I kept it as this, that means yh plus yp is going to end up as like a e to the 2x plus b to the 3x plus, I'll change it to c, plus c e to the 2x. These two are just going to combine. And we don't want that because we have something here. So instead, to change the form, I want to multiply by x. So it's going to be cx e to the 2x. Now this is the same case. If my homogeneous solution was, for example, let's say a e to the 2x plus bx e to the 2x, that means my particular solution is going to be cx squared e to the 2x. So I'm going to keep multiplying by x until my particular solution is different to the homogeneous one. So after getting a guess, what we do is we find y dash of p and y dash dash of the particular solution. We substitute it back into this formula. So what that looks like is, after guessing cx e to the 2x, since this form is already in the homogeneous solution, we diff it twice and we put it into our ODE here. And then we let it equal to the right hand side. Simplifying, we can find that by equating coefficients, c is going to be minus 10. So our particular solution ends up being minus 10 x e to the 2x. That means our solution, which was yh plus yp, is given by a e to the 2x plus b e to the 3x minus 10x e to the 2x. But we're not done because we want to substitute our initial values in by just putting 0 equal to 1, diffing and putting 0. We get two simultaneous equations to find a and b, and putting them back into our general equation here, we get the final solution for the IVP, initial value problem. So the general gist was, we make the characteristic equation first, we get the homogeneous solution, we make a guess to what the particular solution is going to be, and it has to be in a different form to a homogeneous solution. We put the particular solution back, we find this constant here, and then we substitute our initial values in to find a and b. And that gives our final answer. Is that all good? Alright, now that is ODEs done, we're going to be looking at the second half.
Okay, guys, so on to the second part of the seminar, which is Taylor series and the last part, average value of functions and so on. So let's first go on to Taylor series. Let's start by defining a sequence. So a sequence is basically, you can think about it as a function with its domain always being the natural numbers, and its codomain can be any real number, depending on what the sequence is defined as. So the general notation that we use is those curly brackets with AN, where AN gives essentially usually the general formula of any term in the sequence. So sequences are usually defined by rules which tell us how to find them. For example, it can be given in this form, which we call closed form. Right, so usually closed forms are generally more useful than something like this one, which is a recursive form, in which you can only find the current term based on previous terms. So usually if you're given the series in this form, you want to first convert it into closed form to be able to use it. Right, so why are we interested in sequences? In this course, we mainly want to discuss its convergence and divergence. So we call a series convergent if it approaches some finite number L as n approaches infinity. We notate it using limit n approaches infinity, an is equal to some number L. So then we say that an converges to L. And a sequence that's not convergent is going to be divergent. So, right. So, because we know that sequences are very similar to functions, we can also write that if a sequence which is given by this formula, and the formula, the limit for this function exists for very large n's, then we can write that the sequence is also going to converge, similar to how the function converges. Right, so basically comparing sequences and functions. So let's get on with an example. We want to determine whether the sequence converges or diverges as n approaches infinity. And if it converges, we want to find its limit. So essentially, a lot of these questions are similar to 1-141 and 1-131, where you were asked to find the limit of certain things. And recall that if we're given something in this form, where you have a square root, and this essentially, as n goes towards infinity, is going to become infinity minus infinity, right? Which we cannot evaluate because that's indeterminate. So a trick to doing these problems is usually multiplying this thing by its conjugate. So to keep this value constant, we want to multiply it by a fraction where top and bottom are both its conjugate. So therefore, we want to multiply this by n squared plus 3n plus 3 plus n over root n squared plus 3n plus 3 plus n. We want to multiply that to the original expression, such that this keeps the original expression constant, but allows us to simplify this into something that we can determine the limit of. So this is going to become, the top using difference of squares is going to be n squared plus 3n plus 3 minus n squared. Bottom is root n squared plus 3n plus 3 plus n. And this is just 3n plus 3 over the entire thing on the bottom, which we can actually evaluate the limit of this as n approaches infinity, because when n approaches infinity, we can divide top and bottom by the highest power terms, which is usually how you find these limits, which then is going to be the same as limit n approaching infinity of 3 plus 3 on n divided by root 1 plus 3 over n plus 3 over n squared plus 1. So notice how we've divided everything by n, which is the highest power. So therefore, as n approaches infinity, all of these terms are going to equate to 0. So this is just going to be 3 over root 1 plus 1, which is equal to 3 over 2. So we know that the limit of this as n approaches infinity is going to be 3 over 2. And since it actually has a limit, it definitely is going to converge. So here's the answer. Yeah, so typically these are really similar to limit questions. So if you want to find different examples or questions, you can just look at the 1141 textbook. Right, and because we know that sequences are essentially a type of function, except we just notate it differently, we can actually add sequences and multiply them as long as they have the same domain to produce a new sequence. So for example, this is going to be a valid operation. You can think about it just like a function. But note that they must have the same domain, which they usually do because it's going to be natural numbers. So if two sequences are convergent, then we know that the limit rule is going to apply, i.e. the limit of n approaching infinity product of the sequences is just equal to the product of their limits. Right, so this is pretty intuitive. Just note that if the sequences are divergent, then we wouldn't be able to evaluate what their limit of their product is, because that wouldn't be properly defined. Right, so here's a very useful chart telling you the order of growth of different functions. this is not really useful in proof. It's more probably like multiple choice or selection or something. But you can use this to kind of determine whether you think a sequence is going to converge or diverge. So basically the idea is if you're given the sequence of a form of fx on gx, and you know the respective order of growth of fx and gx, and for example, if fx is much greater than gx, then you know this is not going to converge. Yeah, but that's just kind of like an intuitive test. So you can't really use it as a basis for any arguments. You just kind of use it to do a sanity check for yourself. Okay. Yeah, so typical functions, I think most people would also find this intuitive, but this is just, this is something called the super exponential function, where it just grows even faster than normal exponential functions because the growth rate is increasing as n is increasing as well. Yeah, I think you can also find this on the textbook. Right, so pinching theorem for sequences. If we suppose that an, bn, and cn are all sequences, and that we know this inequality is satisfied for all positive integers n, then by the pinching theorem for sequences, we know that bn must also converge to some value L if an and cn both converge to L as n approaches infinity. This is basically just pinching theorem, but adding it for sequences. Right, so another test for convergence is if we can determine whether a sequence is monotonic. So for example, if it always increases, always decreases, or it's always non-increasing or non-decreasing for all of its n in the domain, then it's a monotonic sequence. And a sequence is bounded above if there's some real number m such that all of the terms in the sequence is going to be less than or equal to m for all natural numbers n. So this is essentially the concept of suprema. And we call a sequence that's bounded below if there exists some m such that all of the terms in the sequence is always greater than this m. Alright, so if the sequence is a bounded monotonic sequence of real numbers, then it converges to some real number L. So notice how you have to prove both of, it satisfies like both of these conditions. And we can broadly categorize different divergence of sequences. So they can diverge to infinity or diverge to negative infinity, or be boundedly divergent or be unboundedly divergent. So an example of boundedly divergent sequences is, for example, like sine x. Yeah, where you know it's always bounded between -1 and 1, but we cannot evaluate the limit as it tends towards infinity. So it's going to diverge because it doesn't converge, but it's bounded. There's also unbounded sequences. For example, -1 times n to the power of 2. We don't know what this is going to diverge to, so it's unbounded. Right, the concept of supremum and infimum. So basically what is supremum of a sequence is its least upper bound. So it's just a number that that satisfies all of the terms in the sequence has to be always less than or equal to this number. And if all of the sequences in this all of the terms in this sequence also happens to be always less than or equal to some other number, for example k, then we know that k must be greater or equal to m. So therefore, this is just the smallest number that we can find that satisfies this criteria. And similarly, the infimum of a sequence is just its greatest lower bound. Usually, they're pretty easy to find. So let's do an example. So find the supremum and infimum of the following set where the sequence is defined by this formula. So note that usually you have to use different tests given a formula of a sequence. But for example, if we're given in this form, then as you can see, it's really easy to see that we can just evaluate its first derivative to see if it's monotonic, right? If it's monotonic, decreasing or increasing. So if we let fx be equal to 1 plus x squared over x, or fn, then f dash x is going to be equal to 2x times x minus 1 plus x squared divided by x squared, which is equal to 2x squared minus 1 minus x squared, which is just x squared minus 1 over x squared. So note that when n is equal to 1, 2, 2, 3, and so on, this is always going to be greater than 0, which means that this is a monotonic increasing sequence. And because it's monotonic increasing, we know that its infimum is just going to be the first number in the sequence, which means we take n equals 1 and we evaluate it, and that gives us 1 plus 1 over 1, which is 2. So we know that 2 must be its infimum because all of the terms after this is going to start increasing. And because we know this is monotonic increasing, it obviously is not going to converge. So therefore, there's no supremum because it diverges to infinity and positive infinity. So here's the reasoning. Notice that they just said strictly increasing, but if you want to prove that, you kind of have to just evaluate its first derivative. Right, so what are series? It's important that we don't confuse sequences and series. Basically, series is just sequences, but you add them up. So it has this operation summing up. And it just represents the partial sum of a sequence up to whichever term you write at the top. So this is the upper bound. So for example, this partial sum Sn represents the sum of terms up to n for this sequence An. If the partial sum approaches some finite number L as n approaches infinity, then the infinite series is summable and we say that it converges to L. Whereas if it doesn't approach some finite number, then it diverges. So it's really similar to sequence definitions. And because they're very similar to sequences, we can also interpret them similar to functions. So we can also add different series, subtract them, multiply them by a real constant, and the rules are as listed. I think these are intuitive things, but you just make sure that they have the same lower bound and upper bound. Otherwise, the domain is going to be different, and this wouldn't be valid. So for finite sums, the first n terms are irrelevant to the convergence of a sum. So basically what this means is that if an entire series from 0 to infinity converges, then we take any, essentially you can think about it as section of that series, and they would also have to converge. Because if we just draw a quick graph demonstrating this, for example, if you have a series that when translated into a function looks like this, and let's say the entire series obviously actually, let me draw this a bit better. Let's say we have a series like this, and it actually converges. Then we know that this just represents some section within this series. So if the entire thing is convergent, then we know that part of it must also be contained within, and thus convergent. Right, so up to different tests for the convergence and divergence of series. First of all, we have the kth term test. So note that this one does not test for convergence. This one also only tests for divergence. So basically the idea is that if the term in the series does not approach 0 as k approaches infinity, then the series is going to diverge. Yeah, so basically it's just going to keep on increasing and therefore cannot converge to some real value. Note that the contrapositive is not true. So if the series converges, if the series converges, actually it is true. Contrapositive is true, but the what's it called? The what's the other thing called? Converse is not true. Yeah, the converse is not true. So basically you cannot say that if ak approaches infinity as k approaches infinity, then the series is going to converge. So this is not true, just be aware. So an example would be harmonic series, for example 1 plus 1 on 2 plus 1 on 3 and so on. The last term is 1 on n, right? That's the nth term, but this does converge to 0, whereas the entire series is actually divergent. So therefore, just be aware about this for the kth term test. Right. And we also have something called the comparison test, where if you know that for every term in a series, if it's bound between 0 and another term from another series, then you know that if the other series converges, i.e. its upper bound converges, then this series is also going to converge. And if the lower bound for bk, which is ak, diverges, then we know that this must also diverge. Okay, so a p-series test is very useful in some scenarios, where basically if we have something given in this form, where you have k to the power of p, and p is some real number, then this series is going to converge if only if p is greater than 1, and it will diverge if p is less than or equal to 1. So this is built upon essentially the integral test that we'll mention a bit later, because if you recall from 1,141 and 3,1, if you have an integral in this form, 1 over x to the power of p, This is going to converge only if p is greater than 1 and diverge if p is less than or equal to 1. And you can actually just integrate this and then prove that yourself. Okay, so let's apply this in a question. Suppose that the series n from 0 to infinity of an is a convergent series, with each term being greater than 0 for all n. First of all, let's find its limit, limit of an as n approaches infinity. So because we're told that it's a convergent series, we know that the limit must always approach 0. The last one must always approach 0. Secondly, we want to use the nth test, or basically the cake test, to show that the series of ln an diverges. So here we have to essentially use what is given to us. So if the limit of an as n approaches infinity is going to approach 0, then we know that if we draw the ln graph, which looks like this, and it intersects here at 1, you know that this represents an, by the way. So if an tends towards 0, we know that ln of that is going to approach negative infinity. So this thing is going to approach negative infinity, and therefore we know that this series must diverge. Right, part C. Given that fx is equal to x minus ln 1 plus x is positive for all x being greater than 0, determine whether this series converges or diverges. So essentially, we want to start by using what is given to us, i.e. this statement. So we know that this function is always positive, right? That is 1 plus x is always greater than 0 for x greater than 0. And by rearranging, we have ln 1 plus x is always less than x for any x greater than 0. So notice how if we sub in x is equal to an, so each term in this series, we can actually get an inequality, that is ln 1 plus an is less than an. And this is true because we know that all of the terms in this series are defined to be greater than 0. So this does work because it also satisfies this. So therefore, we can actually just set up an inequality in terms of this. So we know that this series from n is equal to 0 to infinity of ln 1 plus an must be less than the series of n is equal to from 0 to infinity of an. And we know that this, as told in the question, is a convergent series. So therefore, because it's also an upper bound for this series, we know that this series must therefore converge. Right, and that is just a typed up solution. So it's essentially saying the same thing, but you can have a read. Right, so yeah, note that here we're using a comparison test. Okay, so an example of P series. State whether the following is true or false. And we want to say, essentially what the statement is saying is that this series is going to diverge if S is equal to 4 and 3. Where if you notice, this is actually in the exact same format as our P series test from definition. And we know that it will only diverge if P is less than or equal to 1. Whereas S here, which is equivalent to P in the original definition, is greater than 1, which means it's actually going to converge. So this statement is going to be false. Right. Okay. And next one, the integral test. So this is a very useful test. Basically, you can replace the formula for the series with fx. And if fx is a continuous positive function that is decreasing, so this is important, it wouldn't work otherwise, then we can use it to apply the integral test, where if the integral of 1 to infinity of fx dx converges, then so does the series, whereas if the integral diverges, then so does the series. So basically, this is built upon an inequality where you have the integral of 1 to infinity fx dx is always less than the series from k equal to 1. Well, actually, let's use x. Ax is always less than the integral from 1 to infinity fx dx plus f1, where you can actually prove this using Riemann sums, so you can draw out the graph. But yeah, this is the basis upon which this entire integral test is formed. So we can just apply it in questions. And we also have the ratio test. So the ratio test is very useful when you're given something in the form of fx on gx, where you're able to evaluate the ratio of their coefficients. And if this ratio is less than 1, then the series is going to converge. If it's greater than 1, then it's going to diverge. If it's equal to 1, then this series, like this test just doesn't tell us anything about the series. So we cannot use it. So why is this? Is because if the ratio is always less than 1, that means the next term is always decreasing than the term before, right? Which means it's going to eventually converge. Right, question 5. By using an appropriate test, we want to determine whether each of the following series converges or diverges. So if we look at this one is actually given in the form of fx on gx, where it's just essentially x squared onto the power of x. And this matches the ratio test's typical question form, which means we can use the ratio test. So notice the ratio test, we only care about the coefficients of each term. Actually, hang on. Not coefficients, actually just the term itself. So coefficients comes into play a bit later on. So we're just comparing the terms. So we want to find as limit n approaches infinity, the ratio of an plus 1 on an, in which if we substitute the formulas, we will get, this is equivalent to n plus 1 squared on 2 to the power of n plus 1 multiplied by 2 to the power of n on n squared, just by substituting the formulas. And this is going to simplify to, first of all, these cancel out, so leaving just a 2 on the bottom. And this is essentially just a half multiplied by n plus 1 squared on n squared. So if you use limit techniques and divide this term, top and bottom, by n squared, which is its highest term, you get the limit of this is essentially 1 as n goes towards infinity, so the overall limit is just equal to a half. And notice that using the ratio test, this means that the ratio is equal to a half, which is less than 1, which means that the series is going to converge. Yep. Right, so here's the formal layout. Right, question 2. We want to evaluate whether this series is convergent or divergent. So usually when you're given something of this form and you see that if it's very easy to integrate the equivalent integral, then we want to be using the integral test because that's just the simplest way of doing it. So we notice that this is actually very easy to integrate because we can just let u be equal to L and k, where you see that 1 on k is actually just the derivative of u. So therefore, we can transform this. We can compare it to the integral of from 3 to infinity. Let's use x ln x squared. 1 on that. So if we let u be equal to ln x, we change the bounds. So that becomes ln infinity, which is still infinity, ln 3, and u squared, du on u squared. Right, so this is going to, if we integrate it, is going to be negative 1 on u with the bounds of infinity and ln 3, which becomes, if we put negative 1 on infinity, that's just 0. And the second term is going to be positive 1 over ln 3. So finally, we get that this is going to essentially, the integral, the equivalent integral is essentially convergent. So therefore, we know that this series is also going to converge. Right, so yeah, just note that when you see, when the form of the series is given in fx on gx, where both are relatively complicated functions, you can essentially use the ratio test. That would probably be the easiest. Whereas if you can find the, if you can easily evaluate the equivalent integral of it, then you want to use the integral test because that's easier. Okay, so Leibniz test for convergence. This is only for alternating series. So basically an alternating series is just when you have terms that have alternating signs, and we can shorten it using this notation. And an alternating series, according to Leibniz test, will converge if the positive versions. So note that we only care about the absolute value of these. We don't really care about its sign in front of it. We only care about the value of the term itself. So if these satisfy that each term is greater or equal to 0, each term is greater or equal to the following term for all of the k-nth domain, and also that the sequence, if you list it out, eventually converges to 0, then we know the alternating series will also converge. So we call a series absolutely convergent if we take the absolute value of that series and it's also convergent, then it's absolutely convergent. And absolute convergence obviously implies convergence. If it's not absolutely convergent, but you know it converges, then we call it conditionally convergent. Right, so determine whether this series is absolutely or conditionally converges. convergent or is divergent, and provide reasons. So given any series, if we want to prove it diverges, we want to be using the kth term test, in which we can see that obviously this is not going to diverge, because as n approaches infinity, this actually approaches 0, right? So the kth term test doesn't really work here. And we want to essentially then prove its convergence. So how do we prove its convergence? Is we can use the integral test. Right, actually, we use the integral test. Well, you don't have to. You can essentially just use Leibniz test and then prove each of the 1, 2, 3 as it's stated. So first of all, we want to prove that the absolute value of each term in the sequence is always greater than 0. And this is very easily seen because, as you can see, n is a positive number. And ln is always also positive for n greater than 1, right? And n starts from 2 here. So each term in the sequence, its absolute value, which is given by 1 over n ln n, is always greater than 0. So they're always non-negative. Right, so this satisfies the first criteria. And then we want to be looking at if ak is always greater than or equal to ak plus 1. So let's write out ak and ak plus 1. So ak is given by 1 over k ln k. Okay, ak plus 1 is given by 1 over k plus 1 ln k plus 1. And it would be pretty easy to see how this is always going to be greater than this, because you see how the denominator of this is always less than this for any natural numbers k, right? So therefore, when the denominator is bigger, the actual fraction is smaller, so we can get that ak is always greater than ak plus 1, greater or equal to ak plus 1, which satisfies the second rule. And finally, we want to find the limit of this as it approaches infinity, which we've just said is going to be equal to 0. So therefore, by Leibniz test, this is going to converge. We want to then determine if it absolutely or conditionally converges, which then you can just take the absolute value and use the integral test to determine whether it actually absolutely converges. And as you can see, because this is actually going to diverge, the integral is going to diverge, so it's going to converge conditionally because it doesn't converge absolutely. Okay, up to Taylor series. So Taylor series are essentially just infinite sums that help us approximate functions based upon the idea that tangents are valid approximations at a certain point. So it's given by this formula, which is on the textbook. Alternatively, if you want to find the Taylor series of something, you can just enter Taylor command in Maple and it'll help it find for you. Right, so the nth Taylor polynomial for a function near x is equal to a is defined by this, where the Maclaurin series is basically Taylor series where we take a is equal to 0. Alright, so what is Taylor's theorem? It's basically a theorem saying that when we approximate a function f using a Taylor polynomial, we will have a remainder, and this remainder essentially is the error in approximation using the Taylor polynomial. Right, so this remainder has two forms. One's called the Lagrange form, which is given by this. This is also on the textbook. So note that because this remainder approaches 0 as the limit and approaches infinity, this entire thing approaches 0. This means that as we increase the power of the polynomial, we're getting closer and closer to the true value, basically saying that the error in approximation gets smaller and smaller as n gets bigger. Right, so here are some classic examples of Taylor series. So it's good if you can memorize these, but if you can't, they're also listed on the textbook. Right, so what is a power series? A Taylor series is just an example of a power series. It's basically a sum of integers powers of x with some coefficient. Right, so the convergence and divergence of power series depends on the values of x. So we actually have to, some questions will ask you to find the values of x in which it converges or diverges. So if a power series of this form converges for all the points in some interval from negative r plus a to r plus a, then r is called the radius of convergence. So notice that a here, we can kind of think about it as the center point of this power series. And as long as you are within the radius, which is just r and negative r, then you will be converging in this interval. So note that this can be equivalently written as x minus a, absolute value, is less than r. because this is the same thing as x minus r is less than positive r but greater than negative r, and then you rearrange it to get the interval. Right, so how do we find the radius of convergence? Is basically just equivalent to the absolute value of the coefficient of the kth term over the k plus 1 term. Yeah, and the power series will converge absolutely whenever you are within the radius of convergence, and it will diverge outside of that range. Right, so for 1, 2, 4, 1 people, if you want to test at the endpoints, you just substitute the values for x at the endpoints, and then you can use one of the tests mentioned above, like the integral ratio or whatever, to test whether it actually converges or diverges at the endpoints. Otherwise, we'll be finding an open interval in which for this series. All right, so find the open interval of convergence for the power series of this. So note that given this power series, actually not in the exact same form as we are given here, because note that the coefficient of x here is equal to 1, whereas the coefficient of x here is equal to 2. So we don't want that. So what we do first is we want to put it into the form that we're given in, such that we can use the definitions. So then we can pull out a 2 to the power of k. So this is equal to k from 1 to infinity. 2 to the power of k, so we factor that out, that's going to be x minus 7 over 2 to the power of k divided by k squared. So note that here a just takes the value of 7 on 2. And we want to find the open interval of convergence for this power series. So basically what we do is we use the radius of convergence formula, where this is going to be equal to, if we take, that's just the absolute value of coefficient ak over ak plus 1, and taking the limit as k approaches infinity, and that's just going to be equal to the limit of that 2 to the power of k over k squared multiplied by k plus 1 squared over 2 to the power of k plus 1. So for some reason this pencil is malfunctioning, but anyways, that is, after simplification, going to become k plus 1 squared over k squared multiplied by 1 on 2. And note that this is highly similar to one of the questions that we did before, where the limit of this just is equal to 1. So therefore the final radius of convergence is actually just equal to 1/2. And because we know this series is centered at 7 over 2, then we add a minus 1/2 from 7 over 2 to find the open interval. So its upper bound is essentially going to be 7 over 2 plus the radius of convergence, which is going to be 4. And the lower bound is going to be 7 over 2 minus 1 over 2, which is just 3. So therefore we know that the open interval of convergence, notice how we used curly brackets, is going to be 3, 4. Hopefully you can read this. But yeah. And manipulation of power series. So within respective intervals of convergence, power series can be added and multiplied, and also differentiated and integrated by definition. Yeah, a side note is that some questions will sometimes ask you to find the restrictions on x for this series to converge. Then you are taking the entire term and then evaluating ak over ak plus 1, including the x terms, and then you are letting this be less than 1, because we want the radius to be, essentially we want r, using a ratio test, to be less than 1 for it to converge, and then you will be able to find the restrictions on x. Right, and up to the question. So write the Taylor series for fx is equal to sine x squared about x is equal to 0. So because the Taylor series for fx is equal to sine x is a known result, which is x minus x to the power of 3 on 3 factorial plus x to the power of 5 on 5 factorial minus x to the power of 7 on 7 factorial, and so on. So notice the bottom is just basically we're just taking the odd power terms with alternating signs. Right, so we can actually just sub in fx squared. Right, so this is going to become x squared minus x to the power of 6 on 3 factorial plus x to the power of 10 on 5 factorial minus x to the power of 14 on 7 factorial, and so on. And state its radius convergence. So if you use the ratio test, where you'll be able to find sine x squared essentially condenses into this, right? So using the ratio test, you can find that this series actually always converges. So if it always converges, then the radius of convergence is going to be infinity. So yeah, so you can just say the radius of convergence is infinite. So the ratio test is not included here. You can do it as a practice. Right, and finally, last section, applications of integration. So how can we use all of that integration knowledge that we learned earlier? First of all, we're introducing something called the average value of a function, where basically the average value of a function is always given by this formula, where you take 1 over the difference between the upper and lower bounds in the interval, and then multiply it by the integral of a to b of fx dx. So what this essentially represents is, notice if you rearrange this formula, you get average value times b minus a is equal to the integral from a to b of fx dx, right? And note that this right-hand side just represents the area under the graph of fx from a to b. So this is essentially, you can think about it as a value such that if you multiply it by b minus a, which is essentially the width or length of this rectangle here, if you find some value, which is the average value, and multiply that, you get the area of this rectangle. Right, so it's essentially this special value of f such that the area of the rectangle is equal to the area under the curve. And mean value theorem for integrals. So if we suppose that f is continuous on some closed interval ab, then we know there exists some c in ab such that it satisfies this equation. So this is analogous to the mean value theorem, where you'll see that for mean value theorem, we can always write this, right, where f just means the derivative of ft is equal to lowercase ft. So by the fundamental theorem of calculus, you can get that this is just equal to fb minus fa. And from the mean value theorem, we get this inequality, right? Equality. So we can we can move the b minus a to the right-hand side to get f dash c multiplied by b minus a, which actually just translates to this equality. So it's the same thing. Right, so what is arc length of a curve? It's essentially just finding the length of a curve. So if the curve is given in parametric form, like this, then we use a formula for the arc length is given by this. So basically, you just diff x and y with respect to t, square them, add them, and then take the square root and integrate from a to b to find the arc length. So the proof of this formula is also given on the textbook. It's using second approximations and so on. But this is not very useful when we're given the function just in terms of y as a function of x. So if we're given in its normal Cartesian form, then we want to use this formula. So notice these formulas are actually pretty much equivalent, except the first one is used for parametric, but we can also parametrize functions normally. For example, if y is equal to fx, then we can let x be equal to t, and y is just going to be equal to ft. In which case, x dash is just going to be equal to 1, and y dash is just f dash t. So that's how you get this formula here. Essentially just by manipulating the original one. So they're all just different forms of the same formula. And let's use this in a question. So if hx is cosh x, where x is between a and b, we define L to be the arc length of the graph of h between a and b, and a to be the area bounded by the graph. So notice that the graph of cosh looks like this, where it intersects the y-axis at 0, 1. So that's briefly what it looks like. So what this question is essentially saying is that if we take points a and b here, the numerical value of this length and the numerical value of this area is equal for this special function. Right, so how can we prove that? So essentially, we want to start by finding the expressions for the arc length and the area. Right, so area is very simple. It's just integral from a to b of cosh x dx. Whereas the arc length, if we use the formula, so notice how here we're given something of the form just in normal Cartesian form, right? So we can actually just use a to b, like that second form, this one, root 1 plus f dash x squared. So what is the diff of this? If you remember, the diff of this is actually just sinh x. So that's h x diff. And that gives us 1 plus sinh x squared dx square rooted. Okay. Yeah, and if you remember the hyperbolic identities, which is that cos squared x minus sinh squared x is equal to 1. And by rearranging this, we get that this is actually just equivalent to cos x squared. So this is going to be a to b of square root cos squared x dx. And we can just get rid of the square root then. So this is integral from a to b of cos x dx. So notice that these expressions are identical, and this is why we can prove that. Therefore, L is always equal to A. Right. Okay. So here is the proof. By definition, whereas f dash theta is just equal to dr on d theta, so we just replace it with r and dr on d theta because these are always given to us in the question, so it's just simpler to use them. Right, so we actually have 3 separate formulas for arc length, but note that they actually all are derived from the same one. It's just that when the curve formula is given in different forms, it would be beneficial to prioritize one of these over the other ones because it's just easier to use. Right, okay, so and surface areas is essentially the same thing. So you can be given the formula in, for example, parametric form, in which you'll be using this one. So this is for parametric. Oh, well. And the second one is just for normal y is equal to fx. Don't know why this is happening. Okay, and the third one is just for polar curves. So you just substitute into their respective formulas, which are all given on the textbook. Alright, so let's do one final question to conclude our seminar. So a right circular cone with base radius r centimeters and a perpendicular height h centimeters is formed by rotating this line segment given by this. So note that this actually corresponds to the second, whoops, okay, wait a second. It's a bit lagging. Okay, so notice that this actually corresponds to our second form, which is y is equal to fx form. So you can actually just substitute it into this formula given by 2 pi times fx and then square root of that. So we just literally substitute that. So notice the bounds are going to be given by from 0 to h. So surface area is equal to, or SA is equal to, from 0 to h, 2 times pi times r over hx multiplied by square root of 1 plus its derivative squared. So what is the derivative of this? Well, it's just a constant, which is equal to r over h. So we are just adding r over h squared with respect to x, so dx. Right, so we can actually first take all of the constants out of this first. So it's going to be 2 times pi times r over h times, we can also take this entire square root thing out, and that just simplifies to r squared plus h squared, square rooted over h, multiplied by the integral 0 to h of x dx. And this is a integral that can be very easily evaluated. So the first few terms just simplifies to 2 pi r over h squared multiplied by square root r squared plus h squared. And the integral is just x squared over 2 from 0 to h. So 0 contributes nothing, so basically it's just h squared over 2. And notice if you multiply all of them, the h squared cancels out with the h squared here, and the 2 cancels out with the 2. So overall, we're just going to get pi r multiplied by square root h squared plus r squared. Okay, yeah, which is basically what they ask you to prove. So notice for those questions, if they do tell you what surface they want you to find, then you just find that surface. But if they don't specify, then consider an example like this. If you rotate this curve about the x-axis, right, you're going to generate something that looks like this. And there's essentially an additional cap here that's generated like this, and that is not accounted for in this formula of surface area, because this surface area only accounts for this part. So if you're given something like this, you might want to verify just in case what the question is asking, and make sure you add this tip yourself if the question asks for the total surface area. But yes, that is the final example of this seminar. And here is a QR code that you can scan to look at the revision worksheets that we have for Math 1231, 1241, also 1131, 1141, and also 1081 if you want to just like maybe more revision on formulas and stuff. And just quickly back to our attendance sheet. So if you could not scan it, it would be really good if you could scan the attendance for today's seminar now. And also, if you have any additional questions, you're welcome to ask after the seminar. But otherwise, that will be the conclusion of this session. So thanks for coming. Sorry, supervision? Oh, yes, yeah. Also, by the way, this supervision day is next Monday. So if you're free during next Monday, just come into campus, and then I think rooms will be posted a bit later on Insta. Yeah. So this is an expression of interest form. Right, cool. So that is the end